a friend of mine told me that there was a paper written that said that presentations given with an American accent have more of an impact than presentations given with a British accent. I don't think that's been peer-reviewed, but I'm just going to stick with it. So very quickly, what we're going to do is I'm just going to go through the history of deep learning in speech. And Sebastian, I hope a lot of you saw his talk yesterday, did a really good job of setting that up. And we're going to talk about adaptation, which is another thing he covered. So this is, just so you understand, this is a bear adapting to the fact that he's running out of ice. This is why I picked that graphic. And then we're going to talk about what I think is coming next. And that's a joke if you were computing in 1989. And actually, my story starts in 1989, but I found out yesterday that it actually starts in 1985. So this is Tony Robinson, the guy you saw up here in the blue shirt doing that panel. I think he's he's probably the most important guy in speech and has been for a long time. And so he's kind of the hero of my story. So in 1989, he published his dissertation, Connectionist Speech Recognition. And until yesterday, I didn't realize that he had talked to Jeff Hinton. But at the same time, in 1989, Jeff Hinton was in Toronto using neural nets for vision, and he had a postdoc there. Jan LeCun was doing a postdoc there, and so a bunch of you here are kind of descendant from that tradition. And I just love the fact. Now I'm really pleased that the intersection happened sooner than I thought it did, i.e., before Tony started working on his PhD. I told you I'd back this up with data. So here's a really interesting thing. So his PhD, these guys were working on vision, and Tony's working on speech, and it wasn't just academic, because at around that time there was the first commercialization of a neural net being used in banks for reading numbers off of checks. And so that got everyone really excited. So when we passed from that academic sphere into the commercial sphere, and you can see this graph was done by extracting topics from NIPS papers from 1990 to 2006. And so you can see right after there's this huge spike and this huge interest in neural nets. And then things sort of start falling apart. And Tony explained why they started falling apart in speech. And that was simply that things weren't scaling. They didn't have the compute power to do what they needed. And the same thing started happening in vision. So I think the VC who was up here yesterday talked about an AI winter. And that's pretty accurate. And so you see that. I wish the colors were reversed, because the winter should be blue. But so you see that people are starting to talk about vector machines and mixture models, and starting to work on those, because they're getting better results faster. They're getting better results faster because they don't need as much compute power, but also because of this adaptation problem that we're going to talk about. So something really interesting happened in 2009. Jeff Hinton, decided that he'd try his hand at speech, and he published a paper with Microsoft that had a huge impact on the speech community. He demonstrated a reduction in word error rate that was pretty shocking, and so suddenly everyone had to start taking a look at these techniques that these vision guys were using, and in fact the transformation was so fast that if we go back, if we could extend this diagram, which is on my to-do list, by 2012, 70% of the ACAS papers used deep neural nets, which is an amazing change from practically zero in 2006. So these are the ultimate heroes of the story. So we have Jeff Hinton in the front, Jan LeCun on the holding the DNN standard. And then behind them is a guy named Andrew Ng, who I'm sure all of you know. And so he published a paper in 2014 that kind of took the whole thing into, it got the press's attention. So TechCrunch started writing about neural nets and deep learning and what it was going to do and all this amazing stuff. And he's kind of responsible for that. And so the speech community is now really, really interested in these techniques. So I'm going to quickly talk about adaptation. Sorry, I thought my talk was 15 minutes, but it's only 10? 10 plus 5 for questions? Okay, you're not going to get to ask any questions. Okay, so adaptation. So as you heard yesterday, adaptation is the big thing that's holding back some of this full plunge into DNNs for acoustic modeling. And so what does adaptation mean? So this is, I'm going to tell you three different cases, 3 examples. So the first is speaker adaptation, which is a really big deal. So you have the entire world starting to speak English. The entire world does speak English with lots of different accents, lots of phonetic background that is not native. Most of the training corpora is native. And as you know, you need training material in order to get good results. So because we can't do this terrific adaptation, that's a problem. The corpora is also primarily male, so adapting, you need to be able to adapt to females. And the last thing, of course, that all of us individually have different equipment, so we produce sounds differently. That doesn't mean that we aren't getting terrific results. It just means that lots of edge cases are not being covered. The other one, the vision people deal with all the time, and that's noise. And there are techniques for dealing with that, but that's another type of adaptation we need to deal with. And then of course, in speech we have attenuation. People moving away from the microphone, people moving around a room. That's a problem that we have to deal with on a pretty regular basis. So that covers adaptation for acoustics. Then there's, of course, in the language model area, we're finding that you actually don't need as much adaptation, although it is very, very helpful, again, in these edge cases. But we're getting incredibly good results using RNN language models. So you just put a pile of words together, and that's usually enough to get better results than we were getting before with trigram language models. So this is just a little example. So this is a call center in the Philippines dealing with washing machine repair. So you can imagine if we had an acoustic model that was especially prepared for the Filipino accent and a foreground language model that was for washing machines, we could get really good results. But you can't have foreground language models. You just have to have all of that. All of those words that this person might use in your global language model. So this is my last slide. So I'm really catching up here. So this is an illustration of the bleeding edge. It's a bit gruesome, but my designer just took me very literally when I told her I wanted something to illustrate bleeding edge. And so what's happening now, right? What we're seeing a lot of hybrid work coming out in papers. So techniques from the HMM world being applied to the DNN framework, and we're seeing little incremental results. So nothing really earth-shattering yet. And the other thing we're seeing is crossover techniques from the vision world into the speech world, and that makes total sense since the roots, as you heard earlier, that it's the same. We're starting from the same point, and then sort of the other big area of adaptation is context. It's not something that we're doing a lot. So the dialogue people are doing a lot of work in that area, but in our case, we're just not there yet. But it's something that we're going to start working on fairly. It's sort of the next big important thing to work on. So that's it. I caught up, and you've got 5 minutes to ask me questions. Again, don't make them too scientific because I won't be able to answer.
Thank you very much.